Right, hello, and this is getting on to the last part. This is question 6. So this is what I've drawn on the board. There is the start of it. It says figure 6, which is that shows the two slits in the grating. Label figure 6 with the distances d and lambda. So d is the diffraction grating or diffraction spacing. So d is the distance between these two lines. That's d, and your lambda is so we just make sure this is right. Yeah, I think your lambda is not 100% sure on your lambda. Actually, that's the only part I'm not sure on. It doesn't quite tell you in the mark scheme, so hopefully you've got that right. Really sorry about that, but never mind. You're not going to get the A star. Lose 1 mark out of the 60. It's not going to be that bad. This recording. So 6b, made shambles of 6a. 6b, it says, state and explain what happens to the value of angle d, angle theta for the first order beam. It's a wavelength of the monochromatic light decreases. Now you can see I've wrote 2 equations at the top of the board there. Just move out of the way so you can see. So I'm going to zoom in for you. So this n lambda equals d sine theta is the same as lambda equals d sine theta. Now that is because n is 1, so anything times 1 is the same as itself. N is the number of orders, lambda is the wavelength, d is the diffraction grating and diffraction spacing, sine theta is the sine of the angle, and that's why it's put that. Now it's asking us for 6b, what happens to the wavelength if what happens to the angle theta if the first order beam the wavelength the monochromatic light decreases. So we can rearrange this to get sine theta equals ny, or n lambda over d. Now d is a diffraction grating. All we've done is divided both sides by d. So we've got rid of d on this side effectively, and we've moved it over to the other side, what it looks like. So sine theta equals ny over d. Now if we increase the wavelength, this means that we need more of the diffraction spacing, essentially if you think of it like that, to get the sine theta. So basically if we increase lambda, we increase sine theta. If we decrease lambda, we decrease sine theta. So theta decreases. That's all you need to put for that question. Hopefully I've sort of explained it there. And theta just means the angle. I haven't done that very well, but never mind. So for 6c, what's it asking? It says a diffraction grating was used with a spectrometer to obtain the line spectrum star X shown in figure 7. I'm not going to draw this out. You're going to have to look on the AQA website for this. It says the diffraction grating used to obtain the spectrum of star X had 300 slits per nanometer. Calculate the distance between the centre of the 2 adjacent slits on the diagram. So I'm just going to give you a minute to get onto the AQA website and have a look at that. Not missed anything out? Oh, sorry. The 6C, it's asking you to tick the boxes. So the boxes that should be ticked are 1, 5 and 6. So that is, if you've not looked at the mark scheme yet, it's mercury, 3, 4, 5, helium and hydrogen. Now you can see, if you're looking on the diagram, if you're not, you should be, That's because the star X matches up with the wavelengths, some of the lights in the mercury, helium and hydrogen. They fit the best of the three, so that's essentially why they've been selected. And it says the diffraction grating used to obtain is around 300 slits per millimetre, calculated distance between two adjacent slits on this grating. So if we're told, 6D part 2, part 1 is it? Yeah. So the number of slits per millimetre is 300. So as we know, there's 1,000 millimetres in a metre, so we times 300 by 1,000. This gets us 300,000 slits per millimetre. So we've got the 300,000 splits per metre, slits even. So we can use the formula N, so number of slits per metre is 1 over the diffraction grating. So we switch this around, we got D is equal to 1 over N. So the diffraction spacing is 1 over 300,000, and you can either simplify that or leave it as for that, it's up to you. But that's your answer there. Is that what it says? Yeah. So it doesn't matter which you put, but as long as you put that, that's oh, okay. So it says the calculate the first order angle of the diffraction of line P in figure 7. So we sort of talked about it already, 6D part 2. Sine theta equals my over d. So sine theta equals n, which is 1, times lambda, which is, does it tell us? So let me just find the lambda. 5.500. Where's the lambda from? So I'm just trying to find where it's got lambda. Depending on how you found lambda, it's 560 times 10 to the minus 9. Sorry, I'm not going to bother trying to find out lambda because I just want to get through the questions. Over whatever you get for this, so that's over 1 over 300,000. Might get a bit confusing, but crazy. That means theta is equal to the sine inverse of whatever the answer is here. So we can do that now. See what we get. Sine 9.4. That gets to 0.16. And we sine inverse that, we get theta is equal to 9.4 degrees, I think. You might get 9.6, but it's between 9.4 and 9.6 is what we allow. That's your 6D part 2. That's the end of question 6. Hope you've enjoyed this tutorial video thing, and we'll see you in the next chapter.